So open the GSAS-II software. Once you open, three windows will pop up, in which this is the main window. Make sure in the help menu that you have checked the updates. So in this case, I have my version is updated with a 5331. Okay, so just click OK. Now click on the import powder data, and here there are different format. There are different way through which you can import the powder data. Here I will be using GES format from file. So here you can see in this folder I have three files. One is a XRD data file, another is a CIF file which I have downloaded from COD website, and the third one is a standard parameter file. So basically we need these two files. One is the data file, another is the instrument through which you have done the measurement. So that's a standard parameter file from the instrument. And how to get this parameter file? We can use a standard sample like LAB6 and do the measurement, and from that optimize the parameter. Anyway, moving ahead, click on the data file, open it. So do you want to read this file? Yes. Then it will ask you to load the instrument file, instrument parameter file. So just click on this, open it. And now in the second window, you can see the XRD spectra. In the spectra, only in the low theta range, we can see a high intense peak, whereas in the high 2 theta range, we don't have much intense peak. So I'll be limiting my refinement within low angle 2 theta range. So if you move your cursor on the XRD spectra, you will see this value is around 6.7. And how you know this number? When you move the cursor, you can note. You can see the values over here in the bottom. So this is around 7, and I may go up to here. This is around 29. So what you need to do is come back to the main window and then click on the limit. In the limit, define origin T minimize 0.9. So I would like to define it as a 7. And then origin T max is 90. So I would like to define it as a 29. That's it. So minimize the green and the maximize red. Now again, click on the background. Once you click on the background, only the selected 2 theta range will be visible and other part become invisible. And in this case, now you can click on the home button, and now this is your XRD spectra, which you are going to do the refinement. Now coming to the background, in the background, there are various polynomial can be used to fix this background part. So here I'll be using the standard one, and then number of coefficient I'll be choosing maybe around 10. We have maximum 36. So it depends on how bad is your background. So anyway, we can start with say number 10, and we'll see later if we need to increase this number. And after this, we'll go back to the import option. In the import, click on the phase. In the phase, you can choose various options through which you can import the phase. And I'll be choosing from CI file. Click on CI file, and this is my CI file. I have downloaded using COD website. And if you don't know, I have given the link in the description to see how to download CI file of any compound. So open it. Okay, do you want to read this file? Yes. So it takes a while, and then okay, so enter the name of the new phase is CTW04, and select the histogram to add new phase name filter. So this is the histogram, and if you have more than one, you can select all, or you can choose apply strike something. So let's see, because we just have one, so click on OK. Now you have CTW4 phase. And now in the CTW4, you will find there are so many different tabs. So basically important for us is the general, data, and atom. So what is in the journal? Journal has ABC space group. And then you go to the data tab. Here you have option for phase fraction, size, and strength. What is phase fraction? If you consider that you have XRD spectra from composite material, if it's a composite means you have more than one compound in your sample. That means you may have, for example, a composite of say nickel oxide and CdWO4. So nickel oxide maybe 40%, CdWO4 maybe 60%. So how to know it's 40/60? You can choose the option phase fraction. I'll upload another video in near future about how to perform retro refinement if you have more than one phase in a sample in XRD data. Okay. So and then is a size and macrostrength. I will come later on this one, and then we go to third option is atom. Now in this case is a CdWO4. So we got one tungsten, one cadmium, and two O1, two oxygen atoms. Our oxygen atom with different Cartesian coordinate XYZ. So we have XYZ coordinate, we have a fraction, and then we have thermal parameter. These three parameter we need to optimize to improve our refinement. How to do that one? You can simply click over here and a few options pop up. Now if you click on X, it will help you to refine XYZ. If you click on XU, it will help you to define both XYZ and the thermal parameter simultaneously. Similarly, if you click on the F, it will help you to define the fraction. And if you click on FXU, it will help you to define all these Cartesian coordinate as well as fraction as well as thermal parameter. Ideally, this should be one. So I'll just put it. Okay. Okay. That's for now. And maybe now we can go back to the instrument parameter one more time. And here you can see, because this data is coming from synchrotron, the data has been measured by the synchrotron radiation. So it's a high energy radiation compared to what we do in our in-house XRD, like a copper K alpha or something. For copper K alpha, the wavelength is around 2.56, whereas for synchrotron, in this case, is 0.8266. Anyway, because the instrument parameter has already been optimized, so we're not going to refine them again. And what we're going to do is we may need to refine 0 later to improve the refinement. And 0 is correspond to the shift. Okay. So without wasting further time, go to option calculate. In the calculate, click on the refine. It also has a hotkey control plus R. So just click. Once you click on control plus R, or refinement option, then it will ask you to save the file, give the name. So I'll be giving name test and enter. And now it start to perform the refinement. Now initially you will see refinement result RW 27.679. Our goal is to get this number as low as possible. And for that we will be defining different parameter. So, and you can see after first round of refinement, we can see some changes, right? And I'll perform this refinement one more time, and let's see what happens. Okay, the number remains same. Now, we can look at the reflection list. So this is the reflection list. So we have software has already identified the various HKL plane and their two theta values, and it matches very well with the exponent, means at least number of peaks matches very well with the theoretical and the number of peaks, theoretical number of peaks matches very well with the experimental data. Now we need to improve it. Maybe there is some difference in the full width half maxima. There is maybe a slight shift in the experimental and the theoretical data, and that's what we call the refinement. Try to match them exactly with the instrument file, with the instrument data. With the experimental data. My mistake. Anyway, so again we go back to now CdWO4 and now go to the general tab. In this, you click refine unit cell. So by clicking this one, it will help you to define ABC, calculate, refine. Based on my experience, I would suggest when you are performing retro refinement, choose one option at one time and optimize it first. Once you have optimized it, then you can choose more than one point. Okay. So for example, now we have already refined the unit cell. We'll go to the data and I would like to refine the microstring. Again, go back to calculate, click on the refine. It's time to refine. Okay, very good. Number has drastically reduced to 8.2 and there is no any, you know, all looks good. So no any problems. Load new result, yes. And usually in the beginning, I prefer to refine 2 times for each new option. So refine again and see if there is any improvement. Okay, 8.296, no any issue. And then we go to the next option. Now I will refine the size again, do the same thing, calculate, refine. Yeah, it improves slightly and no any, you know, again do the same as I told before. Check, is there any improvement? Okay, good, all good. Now again I will go back to the microstring, refine one more time. Okay, you see, it improves slightly. Now I will try to choose both size and microstring. Okay, let's see what happens. Refine. So even the number has reduced, but you got a message. Note highly correlated parameter. What that mean? These two parameters are correlated to each other. So it's not recommended right now to refine them in one time. So you cancel. Load new result? No, cancel. So I unclick the size and perform refinement one more time. Okay, it looks good, 8.18. And each time when you do any round of refinement, just note down which parameters are changing. Okay, and now I think I will, along with this, I will also refine the LG mix. What is LG mix? L is Lorentzian, G is Gaussian. So if this is 1, that means is a, I think is a Gaussian. And if it's L, then it's, if it's 0, then is L. And if it's between 0 to 1, then is a mix of L and G. So being said that it cannot be higher than 1 or it cannot be lower than 0. And what happen if suppose let's say it's 1.1? You see the color has changed, so it's not permitted. Or say negative 0.1, again the same thing is not permitted. So just remember this part. If you the software with the new updates, it become more user friendly and the creator is trying to improve it further so that even a new the first time user also can easily go through each and every step and try to improve his refinement. Okay, anyway, so I will choose these two and go back, calculate, refine one more time. And okay, cannot because no highly correlated parameter. Okay, cancel. So stop here. But I can choose one independently. Fine. Okay, looks good. I hope it will be 1 or less than 1. Okay, no change, no change at all. One more time. The refinement process takes a lot of time, so you need to have a patience. And then now let's move to the next step. Okay, I think it looks good. So I'll go to the atom. Now in the atom, I will start with refining X, Y, Z first. Okay, so I choose X, 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 X. So we'll refine the Cartesian coordinate first. Calculate, refine. I hope there will be no any issue. Okay, so no much issue. But just remember there is not any drastic change in the number. Okay, slight change, no problem. And now maybe I will try to refine the fraction. So F, 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 sorry, F. Okay, good. Good to go. Calculate, refine. Can I? Good, good, good. No, 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 no. Correlated. Cancel. So one by one. Okay, let's see what happens. Good to go, good to go, good to go. Yes, okay, no problem. So it's improved further, and we can see, yeah, there is some slight difference here, cadmium side. So 0 and refine again, calculate, refine. Okay, you need to have some logic whenever you're doing refinement for fraction. As ideally, it should be one. But if his sample is nanomaterial or has some other issues, maybe not good crystalline or have some defect, it will have occupancies less than one, but it cannot be more than one. So if it's less than one, maybe it's correct, it's fine. But if now let's see if we refine and what happens. So this time, okay, it reduced. It also looks good. And how is the number now? Okay, this number is higher, so that means it's not allowed. That's impossible. So just say no. And this was the remain, so I will try to define it. Go, 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 go. Yeah. Okay, good. So no issue. Any issue? Any issue? Oh no. Again, I cannot. Just stop here one. So those people who want to, try to find out the occupancies in their material, I think they should follow some logic. Now we finish XYZ, we finish traction. Third step is thermal parameter. So I will choose U altogether. Let's see if they are not. If they are not correlated, can be refined in one time. Refine. Go, 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 go. Go, go. Yay! Yes, no problem. Any problem? No, 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 no. Oh shit. Okay, see, all these number negative, not allowed. So for time being, I will make it because it's okay. And let's see what happens. So it's fine. And now maybe I choose here FX. Okay, and this one FX again because here occupancy has changed and XYZ. So let's see if they don't have any dependency. Okay, good to go, good to go. No problem. Okay, all looks good. So now we come back to the data and try to refine. Before this, maybe we can go back to instrument parameter and click on the 0. Calculate, refine. Get down, get down. Yeah, 7.5. Okay, no any issue. So now if you check the background, I think it's not fitted so well because here you can see there is a slight difference. So what I can do is maybe go back to background and instead of 10, maybe I choose 15 point and calculate, refine. Yeah, slightly improved. Okay, looks better, but maybe why not try 20? Haha, calculate, refine. And yeah, it's improved slightly further. It's 7.2. Yeah, you can see now it's matching more close. Okay, anyway. So instrument parameter, we need to refine 0. Okay, good. And go back to CDW4. And now here I would like to refine strain one more time. Fine. Go, 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 go. Good. 7.1. Nice. Is improving on each click. Size. Go, go. Click. 7.1. Good. Good to go, good to go. No problem. Okay, let me check about the LG. Help me to improve. Yeah, it's helping. Yeah, yeah. You see, now the other parameters are optimized, so these numbers are also moving. They have very slight contribution, but that's also matter. No. Any good change? No. Bad. Oh, no, 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 it's not allowed, not allowed. I cannot accept it. Okay. So let's see if we can define these two together now. Can I? I don't know. I don't know. No, 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 no. Can I? Okay, let's see. Microstrain energy. We need to try. Need to try. This one, it's getting. Yeah, 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 yeah. It's getting. Yeah, it's better. It's better. Good. 6.8. Very good. Okay. What about the size? One more time. I need to have a lot patience. Yeah, yeah, yeah. Okay, good. Okay, very good. Ah, atom, all looks good. Okay, perfect. No problem, no problem. Yep. So I think this is all, and now we'll take a look. Okay, looks good. Reflection list, and all looks good. You may have a question that why this has slight difference. I think maybe you need to spend a little more time and try to improve further. About this one, I'm sure because this data is coming from nanorod, and nanorod has a preferred orientation. So due to which the intensity is slightly higher for this two plane. So anyway, I hope it helped you to learn. Now next step is we need to export. So we need to export three different files. One file is powder data as reflection list, CSV, and histogram. So let's export histogram first. So as I given test, so H, and then reflection okay, export powder data as CSV. No, what reflection list? Reflection list as a CSV. Okay, so I will give its name L. And maybe if you have a set of CDWO4 like with a different dope CDWO4 material and you want to, this is a pristine CDWO4, maybe you want to use the same lattice constant ABC and XYZ and all those things for other set of samples. So in that case, what you can do, you can export phase as CIF, quick CIF file, okay, and paste CIF. And even you can also use directly gsas.exe file and open it in a new software. I think you can try it, just play around. So now we have exported few file, and now here, if you open this H is a histogram. What is in this histogram file is X value, Y value is the intensity, and is a calculated spectra. And then this is your background. Because we have limited our, remember, I hope you have remembered that we limited our refinement between 7 to 29. So you can see over here, this is 6.99. We start from 7, so you can start to see data coming. Anyway, so this is about histogram and what is there in the list. In the list file, we have all the plane, their D value, 2 theta value, and other stuff. D value is useful if suppose you take a high resolution TEM and you want to compare your D value from HRTEM with your, you know, CDW for sample, and you can compare these values. So you may know whether it's 100 plane or 011 plane if it has a preferred orientation. And then what is CIF file? So in the CIF file, I will have a detail about this parameter. So XYZ, occupancies, and thermal parameter. And also, uh, what is that? Unit cell, ABC. Yeah. And what else? We also have LST file. LST file include all the detailed information about the refinement. So I think you can take a look at this file and try to understand more. And also you can see there are so many file created. Actually, each file is created at each like each time we perform refinement, it create one individual separate file. The advantage of this one, if suppose due to some reason, if either software get hanged and it get closed, or due to some error you see something, you may lose. Maybe you performance a rate refinement showing very good number, and suddenly due to some wrong choices of parameter, it changed drastically, and you want to come back to your original previous state. So what you can do, you just go back to the folder and choose the previous file, and if you can start from here itself, and that's you can consider as a first one, and remaining you can delete. So at the end, this is the file which we need to keep, and all these files we can delete because we have already performed very well. Okay, so this is how you can perform the data refinement. I hope you may have learned something, and if you like it, do share and subscribe, and also suggest if you need any videos on some other topic or some softwares. Thank you very much for watching.